This is a difficult introduction.
What?
It's a very difficult introduction. So today we have Professor Marta Fajardo from our department and IPFN, more specifically gold, right?
Yes.
So Marta is part of a golden generation of people that.
Okay, I see where this is going.
Marta is part of a generation of people that were students here and then came back. So Marta left IST in, I'm not going to say the year, at some point.
Last century.
And then did her PhD at the École Polytechnique in Paris. She has oscillated between Paris and Lisbon. Her research has, as far as I know, always been on extreme lasers, one form or another. Yep. Today she'll talk about part of the European Innovation Council project to build, right?
Yep. Yep. Demonstrates the feasibility.
Microscope at the nanoscale, so a nanoscope. I forgot to say that Marta received a very prestigious prize in 2022,
yes.
which is a very special prize because it was given to duos of people that have collaborated for a significant amount of time between Portugal and France. And Marta was there. So thank you very much for accepting this invitation.
Welcome. All right, so thanks everyone for being here. Thanks to the physics department for inviting me to give this talk. So I'm going to show you I'm going to try to explain what is this European project that I've been leading for the past 2 years, still has 2 years before it's finished. And it's a special kind of project, which some of us know how involved it is to manage, which is a project from the European Innovation Council. So the European Innovation Council has calls every year for blue sky research with societal applications. And what they want at the end of the exercise is to weed out the best ideas that could have transformative impact in society. And their kind of goal would be, this would be a pipeline to produce unicorns. I guess this is what they want in the end, okay? So the project always has to have a pretty applied component, but it is not supposed to fund incremental research. It's supposed to test completely new ideas out of the box. Let's try this a different way and see if there's a path here. And if we develop a path in this direction, then it has lots of potential impact, promises of new things coming up. And so I'm going to start this talk in a way that I've never done before, which is to give you the pitch that I had to do as part of, it's an exercise that people who do these European Innovation Council projects have to do. So I had to give a little pitch to potential investors, even though this is completely still unproven technological breakthroughs in most of the topics. But let's say this works. What is the impact? How would I spin this off to an industrial investor? Okay, so this is the pitch for the introduction. The goal of NanoXCAN is to design, demonstrate a label-free virus imager. And it does so with X-rays. The motivation for this was from the pandemic, the fact that we realized that there was a large moment of confusion where we didn't know exactly what we were dealing with. And we thought we should have, and why don't we have, an imager that is capable of very high resolution on a tabletop, meaning on a facility that is small enough that can be fitting in hospitals or even big hospitals around the world. Why don't everybody, why doesn't everybody or every hospital have access to this? And the reason is that doing imaging of small samples, biological samples, is quite hard and has some limitations. So there are obvious alternatives that you know of, light microscopy. You perhaps don't know, but it can reach now tens of nanometer resolution. Okay, it can be very, very resolved, but only if you do it, if you handle the samples in a very specific way. Only for transparent and manipulated cells, and in the end, you only find what you already pointed to. You cannot find new things. An alternative is electron microscopy. This is the standard for the highest possible resolution, but you can only use it for cryogenic samples that you slice, and this means that you can do it for very, very, it's a very slow process. So again, if you don't know there's something there, you don't know exactly where to scan, it's very slow. Ideally, you'll be able to do X-ray microscopy because it has potentially the best resolution it has comparable resolution, potentially, and still has this transparency effect. You can do tomography with it. Yeah, probably you've all heard of CT scans. However, this potential resolution that you can reach, you cannot reach it with normal X-ray sources. You need a billion euro scale source, like a synchrotron or an X-ray free electron laser, in order to access these types of resolutions with techniques that I'm going to talk about. So the breakthrough that allows us to go beyond the state of the art is 4 innovations. First, there's a digital laser that's being developed at École Polytechnique that can kind of make a digital plasma, or with its interaction, can make controlled interaction in ways that were not possible before. There's patent pending innovation, which I'm not going to talk about, from Hanover, which allows to do nanometric scale X-ray sources. There's an imaging technique that we're going to explore in a little bit more detail that allows us to do imaging with X-rays without lenses, which is something that was a bottleneck. And of course, there's machine learning, because this is going to be imaging with a lot of throughput, and we need to automate everything, and we need to correlate all the images as they are being acquired. So there's all of these advances are going to come into play. Pathways to market, if I'm pretending that I'm selling this. Pathways to market would be, okay, let's see who's providing the smallest tabletop X-ray source, brightest, smallest X-ray source. This is Exilium, but it's a micron scale. So it doesn't reach the types of resolutions that we want to achieve. They could kind of use this as an innovation to upgrade their source. But the full ambition would be much more impactful, because if you look at what exists right now to do very high resolution imaging, those are the techniques with super resolution imaging. And the super resolution microscopes market is very wide, but especially, and this is something that kind of the investors like, is something that is not consolidated. If you look here in this graph, you see that there are like many techniques, and there's no one leading technique. When there's one leading technique, the scientists in all the hospitals know how to use that one. They're not going to switch easily. But if they're all competing, there's no clear market winner. Then there's room for a new imaging technique that can do it in a different way, provides other alternatives and advantages, and then this has room to grow. So I'm going to spare you how you would go from what we here, the point where we are here, from the first proof of concept at the end of the project to a second path in these projects, which is transition to innovation. And then there's another one called acceleration. And the idea is, so with bigger and bigger chunks of money until there's a unicorn. So I'm going to spare you all of that. Just to say that the actors which we put in play are the people who are actually leading the project scientifically. But this is not the way to do it. If you were to generate these ideas to produce a deep tech spin-off, then typically this is one PhD student with supervision from or advice from the seniors that kind of says, I'm going to lead this, I believe in this, and I'm going to try to do this for real. So it's an idea with a lot of potential, and of course it's completely blue sky. And what I'm going to discuss now is all the ways in which this is very, very, very difficult to implement. But the kind of solutions or workarounds we're trying to find out to be able to deliver this in the end, or at least the concept of how, if this is to be done, how can we do this? All right. And before you say I'm completely out of my mind, and none of this ever happens, and these European projects are completely crazy, actually, this is not the first project like this that I did. So this is the third one of this kind of scale that I run. So these are kind of 4 million euro projects with 7 partners, 5 to 7 partners. This is the order of magnitude we're talking about. Typically international affairs, of course. The first one was quite blue sky and in a much more less industrial focused way. With few, it was more scientific. But then, in the meantime, Europe switched to require more and more applied results from these types of projects. And so the second project we did was called Voxel, and the name of my lab is Voxel because of that, because it was funded with that money. They also required this kind of breakthrough ideas. And the idea then was to try to do 3D imaging in a single shot, and we kind of knew how to do that. We had ideas on how to do it because people with whom I collaborate, we had lots of experience with X-ray, handling X-rays in much more difficult circumstances than for normal imaging, because we typically want to image, well, this is what we do in our real life as scientists, is do X-ray sources from very high brightness lasers. We use them to probe very dense plasmas, such as the plasmas in inertial confinement fusion. So this is kind of environments where, you know, everything is exploding. So we know how to do imaging in tough conditions. So we kind of have a lot of expertise in X-ray optics, and we designed a camera that could do this 3D imaging in a single view. And actually, we did a few demonstrations. As usual, you'd never, at the end of the 4 years, have a prototype that you kind of put on top of the table. Is you figure out how to do it. And in the meantime, you have patents that you do. But in the meantime, one of the founders really did pick up one of the people who was working on the project, Ombline. They founded Let's See Imaging, and now she's she's making the rounds, looking for funding and all of that. So this kind of story actually happens. And it's never on the full product, it's always in a fraction of what you discovered. But this is the path for these Pathfinder projects, okay? So this is kind of gives you the overall view. And of course, the most cited thing in this project was none of that. Was actually the unrolling of Herculaneum papyrus that was done, you remember, that was done by some of our colleagues in Rome with these techniques that we were looking at with low dose X-ray techniques. And they kind of made the news everywhere. All right, so back to the NanoXCAN. So what are the building blocks that we need to put in place to have this nanoscope working, or know how it should work, at least within the next two years that we have left. So basically we are making use of these new lasers to produce X-ray generation. In this case is K-alpha generation. So K-alpha is the transition it's an internal transition in the atom between 1s and 2p. So you have to create a hole in the 1s, and then there's spontaneous emission. It decays from the 2p to 1s, and releases a photon of the exact delta E that you have in this atom. And you can kind of tweak how efficiently you do that by producing a plasma that has the right conditions. So what you want is to have electrons that are able to knock off these interior shells. And you can kind of play with the distribution of the electrons by playing with the way that the plasma is heated. And this is why you need pulse shaping in your laser, so that you can shape how you produce the plasma. Then you have to go through with the X-rays you generated through a sample and go into a detector. And you need to figure out a way to do imaging which is not the classical imaging. So the X-rays that you have in mind are the ones where you have a machine, you're in front of it, and there's a detector, and you just see a flat image of what went through. You could do it with a point source that is spread out, that's point projection imaging, because basically you're thinking about projection imaging, okay? Just front to back, the rays go through, it makes the line integral of whatever it went through, okay? But there's also imaging with optics, right? And then there's the type of imaging that I don't know if you've ever heard about, which is computational imaging with incoherent diffraction or diffraction imaging. So this is when we make use of what happens to the electromagnetic fields when they're propagating and the way they build up interferences as they're propagating. And this is recorded on a detector and gives a signature that I can recover the object from. Okay, so this is propagation imaging from computational, it's never, what you see in the detector is never an image, okay? It's something that you have to make an algorithm to find out what is the image that is recorded there, all right? Okay, so I told you the goal about the X-ray nanoscope, but now I'm going to talk to you about the first one I did, all right, in the Outlook. But then I'm going to talk to you about the main imaging technique that we're using, this correlation imaging, and then the diagnostics that we're setting up with pseudothermal light sources in order to prove that this kind of can work. And then I'll talk about the ways in which we are implementing optimization of the laser pulse interaction so that we can have a better X-ray source out of the laser. Okay, so correlations. How does this work? So when you want to image small things, what you think about typically is going to be, okay, let's put some magnifying optics in front of it. All right, this is what you would do with visible light. And if you took the optics course, which you haven't if you haven't been in the new program, but if those of you who went through Física Experimental Avançada and did the Michelson experiment and the Fourier optics experiment, those of you remember that there is a limit to how much you can amplify or magnify an image, because there is a resolution limit which is determined by the wavelength of light. So you cannot focus smaller than the ratio between the wavelength and the aperture of your lens. And this is because of Fourier propagation. So these fields that are propagating are kind of losing the higher frequencies as they propagate. And when you use a focusing system, what you get at the focus is the Fourier transform of the object you went through. So this is Fourier optics, and this poses the limit, the diffraction limit, on what is the kind of size of the objects that you are able to see. You see from the Fourier limits that actually you would want to go to very small lambdas, because then you would be able to resolve very small things. The problem is you also need high numerical apertures, meaning that you need to have collection angle, which is very large. And there are no, for the reason that I'm showing here, this is an example of the refractive index of a material on X-rays. And you can see the refractive index is written n minus delta plus I beta, okay? And the delta and the beta in X-rays are very, very tiny. This means you cannot bend the rays a lot. Of course, you cannot attenuate. The beta, the complex part, is how much you attenuate with Bayer's law. And the beta, of course, is small. This is why X-rays are transparent, but you do not deflect a lot. So it's very hard to construct lenses with X-rays. You cannot bend the rays very easily. Okay, but there is a solution. And the solution is what we call coherent diffraction imaging. And its variations like tachography and all of other things that are words you may have heard. So how does this work? It's a lensless imaging thing. So this means that I'm not limited by numerical apertures of lenses, which in the X-rays are on the order of 10 to the minus 3. So whatever you gain here in lambda, you lose here in 10 to the minus 3. Okay? This is not a good gain, unless you play with the tricks that we did in the previous project, for which we had this patent that I showed. But anyway, apart from that, typically you have very low NA. Okay, but we know that as light propagates through an object, as it propagates, it builds up this interference pattern. And I know exactly how they relate, the interference pattern and the object. The problem is, in between, I lost the phase. So what I record is the intensity. I don't have the phase of the field that's come in. I only have this intensity pattern, okay? So I have the square of the electric field, and I lost the phase. However, it's been shown that if you sample enough your field in the far field, in your detector, if you make sufficient sample, which is over the Nyquist limits, then you have sufficient information through an algorithm to recover the phase. You can make a guess on the phase. It may be wrong, but you can iterate until you converge on the exact pattern that you have. Could only be made by a guess which kind of converges to the right guess on your object. So this is an algorithmic solution, okay? This is not something that you have a polynomial that you reconstruct your object from. You have to kind of refine and find your best optimum, but then if you do that, you really get to very, very nice results. Problem is, I told you, we need to propagate an object and sum up the phases. You need a coherent source. So I'll tell you what I mean by that. But first, just kind of a mental picture of how this works. You have coherent X-rays go through a target. Let's see here the letter D. You propagate for a long distance, okay? This generates a pattern, which is something like this, okay? And we show that this pattern, if you went through these optical classes, you know that this pattern is the Fourier transform of the incoming beam. And then, if you have sufficient resolution, you can have an algorithm to find out what is the object. This was thought to be impossible for non-periodic samples, and for many years, this is all that the synchrotrons were doing, where they were shooting on targets which had crystallographic periodicity, and then they got the patterns, which would call the Bragg patterns, and they inverted it to the object. But this was shown in 2004 that they could actually retrieve this even for non-periodic objects. So this means you start to be able to image anything now, if you know how to solve these algorithms. Okay, but I said we needed for that a pulse, which is a coherent X-ray pulse. Here what you have is LCLS, which is one of the places where we've done experiments. It's an X-ray free electron laser in Stanford. There's another one in Europe. And this is one of those billion dollar machines. This is not going before. So there are other sources, other bright sources. One of them we do at the lab, which is high harmonic generation, but it doesn't go to the hard X-rays, and it's very hard to make it go through wet samples. So this one we are working on, but it's ideally we would be able to use that, but we cannot do it very strongly in the soft X-rays that we required. There are synchrotrons, and there are even other alternative methods with accelerating electrons in plasmas to generate this kind of sources. Typically, these are big facilities. They are able to do the best images that you can imagine. And here, for instance, this was from 2024 tachography result. Tachography is just this coherent imaging scanned. And they reach resolutions which are 4 nanometers. So you see, you can do really spectacular things. And you can do pump probes, and you can do medical imaging, many, many things. So I mentioned coherence. Let me just briefly remind you what it is. So you know when a person is not being coherent is when they're not being consistent with themselves. They're saying something today and not the same thing tomorrow. And then you cannot trust it. So when a light source is coherent, you know by sampling it at a given time how it is in the past. And if you start losing this information, you go into you are beyond its coherence length, okay, as it propagates. This can be seen as temporal coherence, but you also have spatial coherence. So spatial coherence is the same thing, can I predict from knowing the phase here, how is the phase here? Independently, that's the wavelength. So in my example here, this in time, of course, relates to how you are one wavelength shifted away from your initial source. This is when you start to be out of phase. In space, even independently that the wavefronts or the spacing between the waves is not constant, if you force light to go through a very tiny obstacle, then it will make a very predictable shape, okay? And then you know that you can know from this position what is going to be the phase in this position. So it's spatially coherent. So you can have temporally coherent or spatially coherent sources. All right. When you use coherence, then you can do things like the interferometers that you probably used, like the Michelson interferometer. And for the Michelson interferometer, what you're doing is measuring the coherence time of your source by producing interfering fringes and seeing when they go in and out of big contrast in the fringes. And this contrast function is exactly the correlation of the electric field. And so a Michelson is measuring the first order correlation of the incoming field, okay? This first order correlation, which just samples the field against each other in the two arms of the Michelson, is delaying one about the other, okay? And is measuring brightness and peaks and troughs in the intensity pattern. These are related to this first order coherence. But you can also measure the second order coherence. So what is the second order coherence? Second order is when you squared, right? So you can you know that the intensity is the square of the field. So if you measure the correlation of the intensity, then you have a second order correlation, okay, of the field. And the second order correlation, this is related to the Henbrin-Brown twist experiment. This is related to how a light is flickering. Is it changing as a function of time? So if you have a speckle, a light source that is changing in time, or speckle, a light source that is random in space, because we have temporal and spatial coherence, then you can have this kind of second order correlation and test how it goes. And there is this theorem from, I think it's called the Vita theorem, and it relates in optics to the Van Sitter-Zernick theorem, which just says how when you're propagating, which are the frequencies that you're propagating with, and you're kind of building up coherence as you are moving further and further away from a source. So a point source very far away is going to make a very coherent, spatially coherent field. It's kind of relating these quantities. And this theorem relates the second order coherence, if you have an incoherent source, to the first order coherence. So this means that I can get this interference pattern that I showed you that I know how to reconstruct. When I do first order coherence with a coherent field and I propagate, I get the Fourier transform. I know how to do the inversion of that to get an object. But now I don't have a coherent source. I don't have an XFEL, I don't have $1 billion. But I can do an incoherence pattern, and I can relate what I measure here with this relationship, 1 plus the G1. From this relationship, I can recover this pattern. And then I can do the inversions and recover my object. This is the idea behind the imaging technique in this project, is to be able to get incoherent sources to do these lensless imaging techniques that we usually only can do with coherent X-rays. Okay, so in this incoherent diffraction imaging, you lose this nice Fourier transform at the end of your imaging, of your propagation. So if you go with the incoherent X-rays through your D, now you don't have the Fourier transform of the D, you have a speckle pattern, which has, I think you've all seen speckle when you shine a laser at an object and you see these little dots that are bright dots. This is buildup of interference out of a random surface. It kind of makes high and low noise as the interference pattern is adding randomly, okay? But if you do it multiple times, I see this as, let's say, each part of the object has gone through a random phase. And if you just sample this once, you get this random pattern. But if you sample it many, many times, and each time you're going through the same object, but now with a different phase at each point of the object. If you average everything out, the only thing that stays there is the object. So you may be able to recover. Or if you think about it in terms of your known Young slit experiment, you know from this position of the sources, so these are two-point sources, from the position that they should interfere here, if you add a phase shift, they will interfere here. If you now start adding or retrieving random phase shifts, you know that on average where they are pointing, okay? And it's oh, sorry. You're not seeing my, but you see it there, the two, thank you. So you know on average where they're going to point, okay? So you kind of have a trace of what was the original object that went through inside all of those random fluctuations. This is, in my mind, how I picture this. All right, so if you want to do the field correlations, let's do an example. So then you know what you should get. You have a field that is random in amplitude and is also random in phase. So you add a random amplitude and phase field. Then the only thing you did is you said what was the coherence length of this field. You say that this field has an LC of coherence length. Then when you do the cross correlation of this field with itself, this means you say, okay, if I shift it by 1 pixel, how much is the product of these two? By 2 pixels, 3 pixels, you do the correlation, okay? Then it should, if it's completely random, you're expecting 0, but no, actually I told you, it has a coherence length. So they are kind of related by this coherence length. So they're not fully coherent, they're not an image of each other all the time. They have random spikes, but there remains some coherence. And this coherence length you can scan, and it will emerge around the length that I said was their coherence length. But it's still very noisy. So what happens is that I need to do it multiple times. So if I do this correlation, and then I average out all the correlations, sometimes they go up, sometimes they go down. On average, the G2 pattern emerges, the G1 pattern emerges out of this G2, okay? So this is the idea. And this was shown when we were starting the project. This was proposed, actually. There was no solution at the time when we started the project. So with an XFEL, a coherent source, it produces this diffraction pattern that we're used to from a coherent source. And Each one of the samples produces a very speckly image. But then when you kind of convolve all of them, the same pattern as you had here emerges from the noise, okay? And the incoherent source that you're generating is just this decay that I told you from a K alpha. So these guys are just producing spontaneous emission, and the spontaneous emission from this small object is adding up here. And if they're emitted at if they have emitted at the same time, have the same phase, they make a bright spot. If they're out of phase, they make a zero spot. And so you have lots of spots that are random, but then you collect many, 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 you do the autocorrelation, and the Fourier transform emerges out of all those correlations. So that's the idea. And then they did this, actually. They proven this in 23, that is actually this autocorrelation gives exactly what you would expect. So if you make 2 dots, you will make random patterns, but if you do the autocorrelation of all the random patterns, a Fourier transform of the 2 dots emerges, which is an interference pattern, like a Young slit. And then you know how to reconstruct that. And from that, recover the 2 dots. So they were able to recover the 2 dots. And indeed, they have, so this is 1 micron is this big. Can you see my, no. So 1 micron is this big. So they did have sub-micron resolution. Small detail, they also use about 30,000 shots of an XFEL. So we maybe have ways to go in terms of improving our X-ray source. Okay, but the good news is we know how to do it now. So if you manage to get a pattern of speckles, which looks like there's nothing there, but do the correlations, and then from that recover the coherent pattern, which is the Fourier transform of the object, then we know how to work with it. We've been doing this for ages. So I give here 2 examples of 2 works we did with the harmonics, which is a coherent source. And we can do, even in single shots. So you put a little sample. This is the Fourier transform of your little music notes. And then you recover from the pattern, you can recover the object. And we even invented techniques so that we could recover several times the same object with different colors. And we've been playing with this for a long time, so we know how to do it. The problem is we don't know how to do it yet, or we really need to be careful on how to do it with incoherent sources. And this we need to learn how to do. So for learning how to do these speckle patterns and recover the object that is hidden there with these speckle patterns, we turn to mock models, because before we cannot do that until we have a very bright X-ray source which is with the right conditions. And there are members of the group in the consortium who are working on that. But while they're working on that, we cannot wait for them to have this ready to be able to have all the algorithms for reconstruction and all of that. So what we did was, okay, let's try to improve our recognition abilities. Okay, so in this part, I'm going to talk about this part here of the project. So not on the laser pulse shaping or the K-alpha optimization, but once you go through an object and you go with your speckles into the detector, how do you make it so that there's an image in the end? All right, so I said that we're doing these second order correlations, right? So we're doing same pattern, each time a different phase coming in, a different random phase. Do the autocorrelation of each, and from there you reconstruct. You can see that the Fourier transform is there. It kind of shows up. Individually it was just a grainy pattern, but then the pattern emergence out of it. Let's see if this is real. We kind of knew from the equations it should be so. There were kind of couple of papers that said it would be possible, but I'm an experimentalist. Until I've seen it, I don't believe it. So we set up a little station where we would prove it, and of course not with X-rays. We had to do it first with infrared. And so what we did was we set up a diffuser, a rotating diffuser, which is a way to turn our laser, which is coherence. The waves come in all at the same time, I mean very, very coherently, very consistently. But if you go through a diffuser, then this kind of randomizes how much they travel. So the wave that is traveling, that is propagating now, is full of speckle. So it's full of these random grains, okay? And you can also control if you can repeat those grains while you're acquiring your image. So do you have a constant grain? Or you can acquire for a long time and move your speckle, and then you have several grains that are mixing in your picture and making your picture even worse, okay? So this is what Pablo set out to do. So Pablo was the one who did, he's there, was the one who did all these experiments at the Voxel Lab. And the idea is, let's test this relationship, and especially let's test something that is missing here, which is a very important factor that tells us that none of this is going to happen if this goes on for, if you're not able to do the correlation of each sample. And instead, you're correlating different samples in the same image. If you cannot individually do the correlation, if you start to add up things that don't have to do anything with each other, then you lose the information. And how fast do you lose this information? So this is the test we wanted to do. So for that, he first looked at changing the correlation, the speed with which he was rotating. He could tell that the images or the speckles, how they were forming, they were kind of blurring out or popping back up, okay? And do you have nice speckles to be able to do this correlation, or are you fuzzing everything, basically? And so he could correlate this G2 with the speed at which he was turning. So he knows, you know, how much you can afford to lose in terms of number of, basically this concept that I introduced earlier, this coherence length. How can you compare to the coherence length in terms of your integration time? But then he managed to show that indeed so we used an SLM to do that, spatial light modulator, and he could put whatever pattern he wanted. And then what you can see is if you put like the classic 2 pinholes, you get the classic stripe pattern from a Young slit, which is the same that you'd predict in the simulations. And it's kind of there with some hexagonal pattern with a lambda letter. So we're trying this out and see how this kind of kills the signal as we are accumulating more and more random patterns on the detector. And so he made a whole study on how much can I afford in terms of signal to noise for the different types of conditions that I have until I start losing the signal. So basically what we're trying to do is in this relationship that the G2 is equal to 1 plus something G1, he was trying to look for this, what are the laws governing this beta, which worked pretty well. So the second strategy was, okay, we have to live with this, so let's clean it up with machine learning. And so we had a small project with one of the students was, okay, let's clean up these images with machine learning, recognize the pattern behind this noise, try to highlight the pattern and make it better. So one of our students was doing that. It kind of works, as if you train it long enough, it will find out the patterns. And especially, so this is from simulations, but especially what you manage to do is, if you produce a speckle pattern and you recover it, you have not as good image as in the actual coherence diffraction imaging. With incoherent diffraction imaging, it gets worse. Here's the same comparison with the music notes again. But you know that it's there. So now it's a matter of improving, getting better signal to noise, but it's there. So we know this is possible. And so the last piece on this is from from an experiment that we did in January. So the results are not there yet. Mathilde is analyzing. So I'm trying to put as I go along the works, how there were MEFT projects attached to this, or PICs, or even some of those third-year short sessions in the lab that you have from Fui. Some of them were done in this context. Or, which I think is probably interesting for you, in the context of those who are doing PhDs, lab rotations. So this is, person is doing a PhD in one field, but wants to learn a technique for 1-2 months, goes to another lab, and this is credited in the PhD project. And so this is an option to do lab rotations for these kinds of techniques that you want to learn. And so one of the master students, Mathilde's master students, was done at the Synchrotron Soleil, and we were shooting on objects, creating by way of a little diffuser some known speckle patterns, and now she's doing the recovery of what can we tell about this statistics of this source, and can we get all of this progress on imaging. All right, and now just to finalize, let me give you some ways into which, so that I've told you a lot about the imaging part, ways into which we're working on the making a better source part. So as I told you in the beginning, from these projects, all of these advances in themselves are worthwhile. If I have a way to make images with coherent sources, this opens a lot of possibilities. If I have a way to make images, if I make a very bright X-ray source, there's lots of people wanting to do that. So this is something that we would want to have in the end. Are you trying me to finish? Estou em 42, estou a medir. Is it okay? 42 minutes, but I imagine because we started late that you want me to finish early? No? No? It's fine. All right, so I just finished there. So we were looking at the right part, now we're looking at the left part. Can I do donut shapes or whatever shapes to my laser and improve the X-rays that I'm producing? And how can we do this with machine learning? So basically, I was involved in this workshop, and we produced kind of a white book or recommendations for the community type of paper, where we kind of realized from the people who were doing laser plasma interaction that this was going a little bit aimlessly in terms of the data that was being accumulated. Europe was always asking us, record all the data, do the fair data stuff and all of that, so that it's usable by others, but we weren't actually using our own data because we were just like not properly implementing machine learning algorithms in the whole experiment and a data pipeline for the whole experiment. And so we were kind of missing out on some of the opportunities that you could extract from there. So we kind of made, okay, so we said, everybody, now, from now on, we start to have proper data taking. We have collections of data that can be used by other people and all of that, etc. Plenty of recommendations. And we will try to have experiments that can run on their own feedback and improve themselves. This was kind of a couple of things that we decided. So you know we have probably all visited this by now, a small tabletop facility, a small high power laser facility here at IST. Is a voxel station that I mentioned several times. Okay, so this is something that we are running with the students. So this is something that we can play with and do whatever we want. So okay, just to tell you, a lot of the work on plasma physics, so none of this is for plasmas, right? Which is, my group is the group for lasers and plasmas. So this is the bulk of my work, but not for that project. I just want to acknowledge lots of stuff that Gareth Williams is doing, because he's the one who has been doing all the plasma experiments in the group. But the idea here is we have a high power laser, let's use it to do optimization of the source. And we knew there are people publishing results like this with laser plasma interaction. So for instance, these guys here in the UK is where they started all of that. They started having feedback loops on the detectors and making them, so the guys from CERN are looking like, tell me something new, because you've been doing this for a long time. But for us, nobody was doing that. So you see that these papers are not from so long ago, where we start to try to optimize things. And so from one of those lab rotations, Gonçalo Vaz was setting up spatial light modulator, which is an object that can modulate the phase, is the one we used for those imaging tests. And we said, okay, let's do a secondary source of XUV, the harmonics, and see can we optimize the source with machine learning. And so you give it a target, put the brightest possible focus, and move whatever you need to move in the SLM so that my focus is best. Okay? So this is an experiment that we did. It kind of works. It's nothing new. Okay? There's people doing this in other ways, not with this for a long time. But I wanted to mention, because this was also kind of a PIC project, which 3 students were having fun when we were unpacking this. They were having fun setting up several beam profiles and characterizing them. And so they were able to do their own small projects on this. Then you can become more sophisticated, is say, okay, let's do Bayesian optimization. Let's give them the chance to change several parameters in a beam and see which one you need to improve to get the maximum source. And this kind of works. It kind of, you let the parameters free, and it kind of finds the optimum sets of parameters that honestly, so far we would have found ourselves, but it could have been without us. It finds the optimum solutions. But the other thing that these type of machine learning algorithms does is it highlights correlations between parameters that you maybe, as a human with less patience, wouldn't have time to explore. You're kind of trying to explore, okay, I'm looking for the maximum, so I'm going to scan this parameter, then this parameter to find the better, then this parameter. At some point, you're fed up. You're not mapping out the whole universe of parameters. And so a machine that does this automatically and makes predictions on where should I go find next, which is the Bayesian part, then does it for you in a much more systematic way, and then you can find correlations between the parameters that you wouldn't have found if it was you doing this alone. Then there's another project which is putting the whole lab as a machine. So what I want is to tell the lab, do this, and the motors move, things happen, and the jet is fired, the laser is open, goes to the target that has been moved to the right position, the data is recorded, everything is automated. This is the goal. Of course, this is not yet running like that, but for that you need a backbone. And the backbone is some data acquisition system that is able to talk to all the machines in your system and that you're able to make a kind of a brain for. So there was a student who was doing his PhD, his master's with Horacio, who learned how to do all this in and out stuff, who implemented this for our lab, and we use it for the X-rays. So what you see here repeated is the little bright X-rays that are being emitted, and we were making a target that was rotating, and then we asked it to, okay, so let's sample the space of where do I put my lens, how, I don't know, I could have changed the speed of the target, which I didn't, but you know, what are the parameters? Play with the parameters. Our goal is maximum X-rays on the CCD. And so this is one way to do it, okay? So this is what we were playing with at the Voxel Lab, and this is something that, sorry, this one was wrong. I'm now here, don't worry, on the new interaction capabilities. So this is just to finish, to tell you that we're playing with these shapes on how to make the interaction optimized. So far, we can say, okay, the tightest possible spot gives me the brightest X-rays, but there's a room for exploring many parameters. And so there are colleagues in our department who have been thinking about this for many, many years, is, okay, what is the ideal pulse shape in my laser to produce this type of X-rays or this type of particles? And they've been playing with, well, they've been doing this with simulations because the tools, we're developing them now, the experimental tools. But with simulations, they're finding things like, okay, if I have Fusili type beams like this one, beams that have a phase that goes around in time, what happens when I shoot it into a plasma? What happens to the particles? Do they acquire some momentum? Do they go in a particular direction? Do they gain more speed than they would have if I had just pushed them with a basic Gaussian? So all these questions, They're answering with the simulations, but the experiments, there are only 2 that I know of, or it's very basic right now. It's a nascent field. So there is room for doing a lot of things. So I know you went to Marco's talk, and basically the goal of his ERC is to explore these parameters by designing these new lenses. We had also been doing that for a while. So these here I show you. You see the little, oh, it's very difficult to see. Maybe only on this one you can see the spirals. So we had a student who made for her master's thesis, she designed and then printed the lenses with Professor Susanna from INESC, where they have nanofabrication. And so she was able to produce harmonics which had orbital angular momentum and produce like these type of swirling fields, but in the harmonics. With Marco, he had this setup to do these spiral-shaped beams, these structured light sources within IR, and Pablo learned how to implement it, and it kind of works. With our IR laser, we haven't shot at the target with it yet. Right now we're in the shaping of the pulse phase, but these are the latest results from Robert and Gabriela, who's doing this kind of lab rotation that I mentioned from Marco's team, and they look kind of nice. So they have these fields that are shaped in weird ways. Our colleagues in France are doing even crazier things. They have a laser which is made with tons of fibers, 70 fibers or something like that they add coherently. So when the fibers, so everything is a laser, and now you need to put all the lasers in phase, so all the fibers in phase, so that you have one single laser coming out. So when the fibers are not in phase, when they have random phase, you have the speckle that I mentioned, right? This makes these little blobs of intensity, random phase. But then when you start to put everything in phase, then they coalesce into one coherent image. And you have 70% of the energy of the laser here. And this, why is this important? I mean, what a crazy way to do a laser. It's because these fibers, individually they cannot take a lot of energy. But if you put them all together, it makes a very high energy laser, but also they sustain very high frequencies. This means that I can produce a laser which shoots instead at once per 10 hertz or 1 kilohertz, like the laser we have downstairs. This one shoots at the megahertz. So it has millijoule range, but at the megahertz. So this is kilowatt laser, okay? So your laser pointers are milliwatt, so that you can see the order of magnitude, okay? And they're playing with the phase and making the twirl beams as well. And we're designing the tools to make these little things shaped individually. So we're having a lot of fun in these things. This is what I wanted to mention. One last mention, that the detectors are also something that we inherited from CERN. Because now we have to have detectors that are able to do correlations at the rep rate of the megahertz, not for everybody. And so that's it. In conclusion, the NanoXCAN project is very challenging. But it launches so many interesting paths for us to explore that I think that we can have a lot of advances in these different fields that are easy to have some contribution, and we can have a scale here at the lab where we can have training of the students that are able to do these kind of frontier experiments, and basically a lot of fun. So thank you. And this is the lab. And